To determine the shape of covalent molecules, we'll be looking at valence shell electron pair repulsion theory, in short, VSEPR. In VSEPR, the first thing you consider is only the valence electrons. Thereafter, you determine how many lone pairs and bond pairs electrons the central atom has. From there, these electron pairs would actually spread themselves as far away from each other as possible, and that will give rise to the shape of the molecule. Let us take a look at some example. In beryllium chloride, Be has 2 valence electrons, and the process, and when chemically bonded with chlorine atoms, they form 2 single bond, and beryllium has 0 lone pair. So if it's 0 lone pair, 2 bond pairs, the electron cloud in the 2 bond pairs will spread as far apart as possible. That will give rise to the shape linear. In the case of boron fluoride, boron is group 13, 3 valence electrons, and when chemically bonded with fluorine atom, it would have 3 bond pairs, and similarly 0 lone pair. So with 3 bond pairs, 0 lone pairs spreading and the electron cloud to be spread as far apart as possible, it will be trigonal planar in shape. Next, CH4. CH4, carbon is group 14, it has 4 valence electrons. When carbon is chemically bonded with hydrogen atom, you will form 4 bond pairs, 0 lone pair. Therefore, the shape is tetrahedral, angle 109.5. PF5, phosphorus is group 15, 5 valence electrons. When chemically bonded with fluorine, you will form 5 bond pairs, and hence the shape is trigonal, bipyramidal, and the angle will be 120 for this and 90 degrees for this. Last but not least, SF6, which means sulfur is group 16, 6 valence electrons. So when chemically bonded with fluorine atoms, you form 6 bond pairs. Angle therefore is 90. We'll call that octahedral in shape, or otherwise square bipyramidal. For the list of examples that we covered earlier, all the central atoms in these molecules do not have any lone pairs. Let's take a look at what happened when there's lone pair. But before that, in VSEPR, it is stated that the lone pair electron occupy a larger space given its higher charge density. Therefore, the force of repulsion between lone pairs electrons is higher than between lone pair and bond pair, and between bond pairs, and finally between bond pair and single electron. We'll now take a look at examples that cover all these. The first example we're going to cover is when there's 3 electron pairs, and say for example SeO2. So in the case of SeO2, all right, there's actually the structural formula. And selenium, given that it's group 16, it has 6 valence electrons. So selenium would have 1 lone pair. When chemically bonded with oxygen, you will have 2 bond pairs. So with 1 lone pair, 2 bond pairs, the lone pair, which has a higher charge density, exert greater repulsion force on the bond pair. Therefore, as a consequence, this angle here would have to be less than 120 degrees. To be more specific, the angle actually is from 110 degrees to less than 120 degrees. Next example we look at is for 4 electron pairs. Say, for example, in the case of NH3, NH3 would have 3 bond pair, and the nitrogen would actually has a lone pair. So consequently, its shape will be trigonal, pyramidal. As this lone pair electron cannot be visually seen, what one could see is actually 4 atoms arranged in a trigonal pyramidal shape. In the case of water, water would have 2 bond pairs and 2 lone. So with 2 lone pairs exerting greater repulsion force on the bond pair, we expect this angle to be even smaller. So that's the reason why when it is actually 4 bond pairs, the angle is 109. When it is 3 bond pairs, it goes to 107, about 107. And finally, when it's 2 bond pair, it's about 105. And the shape for water molecule is bent. Let's take a look at 5 electron pairs. For 5 electron pairs, we can group the site into 2 groups. One is actually the axial site. The other is the equatorial site. So if there is actually lone pair, the lone pair would want to reside at the equatorial site. The reason is because at the equatorial site, there's only 2 electron pairs that's 90 degrees away from the equatorial site, which in this case are the electron pairs residing in the axial site. If the electron pairs resides in the axial site, then it is 90 degrees away from the electron pairs in 3 of the equatorial side. So it is deemed that axial electron pair is more crowded than equatorial electron pair. Therefore, because of that, the larger lone pairs would occupy the equatorial side. So with that, let's take a look at some examples. So you look at SF4. For the case of SF4, S is group 16. It has 4 bond pairs with 4 of the fluorine atoms, and sulfur has a lone pair. So with 1 lone pair and 4 bond pair, the lone pair would now be at the equatorial side. So therefore, you will end up with actually a seesaw shape. Next, ICL3. In ICL3, you will find that the ICL3 has 3 bond pairs, and iodine would have 4 lone pair electrons. They're not involved in the chemical bonding. So end up is 2 lone pairs and 3 bond pairs. So with 2 lone pairs and 3 bond pairs, this lone pair will again be at the equatorial side. And therefore, because of that, the shape of ICL3 will be T-shape. So we also want to note that the angle here is actually less than 120. Reason is because the lone pair will exert greater repulsion force on the bond pair. Similarly, in the same vein, we don't expect this angle to be a perfect 90. It will be slightly less than 90 because the lone pair occupy a larger area. Last but not least, if you look at I3-, in the case I3-, there's actually a dative bond. So dative bond is considered as a bond pair and with another single covalent bond. So there's 2 bond pair, and in the case of iodine, it has 6 unbonded electrons. So end up with 3 lone pairs and 2 bond pairs. And with that, we know that all the lone pair, the electrons will reside at the equatorial side, giving rise to actually the linear shape. Finally, we take a look at IF5. In the case of IF5, the same way, it has 5 bond pairs with 5 of the fluorine atoms, and you will have 1 lone pair. So with 1 lone and 5 bond, the lone pair will be as sketched here. So therefore, because of this will be a square pyramidal. And finally, we look at XeF4. XeF4, we have 4 bond pairs with 4 of the fluorine atoms, and you have 4 electrons that's not bonded. Therefore, it will be 2 lone pairs and 4 bond pairs. And the 2 lone pairs, which need to be as far away from each other as possible, will be on opposite sides. Therefore, end up the final shape will be square planar.